Picture a place where galaxies huddle together by the thousands, where the fabric of space itself seems to twist and warp under the weight of cosmic secrets. This is the Hercules Cluster, a sprawling metropolis of stars so dense, so mysterious, that astronomers still uncover new puzzles every time they peer into its depths. But here's the thing, this isn't just another distant corner of the universe. Hidden within its glowing embrace are phenomena so strange, so utterly baffling, they defy everything we think we know about how the cosmos works. Think about the last time you looked up at the night sky and felt that flicker of wonder. Now multiply that by 1,000,000, because the Hercules Cluster isn't just about beauty, it's a stage for the universe's most dramatic enigmas. Unexplained bursts of energy flicker like cosmic Morse code. Galaxies move in ways that shouldn't be possible, as if some invisible hand is rearranging them. And then there are the shadows, vast, dark structures lurking between the stars, untouchable by telescopes, whispering of forces we can't yet comprehend. This is why we're here, not just to observe, but to explore, to question, to stand at the edge of the unknown and dare to look deeper. Because the Hercules Cluster isn't just a collection of stars, it's a riddle wrapped in light, waiting for us to unravel it. And over the course of this journey, we'll uncover 25 of its most jaw-dropping mysteries, each one a piece of a puzzle that could rewrite our understanding of space itself. So let's begin. The universe is calling, and what we find might just change how you see the night sky forever. One of the most jaw-dropping puzzles lurking in the Hercules Cluster isn't something we can see, it's something that's not there. Imagine building a house carefully following the blueprint, only to realize entire support beams are missing, yet somehow the structure still stands. That's the kind of head-scratching mystery astronomers face when studying certain galaxies in this cluster. According to everything we know about how the universe works, these galaxies should be packed with dark matter, that invisible glue holding galaxies together. But when researchers measured their movements, they found something impossible: entire regions where dark matter seems to have vanished without a trace. This isn't just a minor discrepancy, it's a cosmic rebellion. Dark matter makes up roughly 85% of the universe's mass, and its gravitational pull is what keeps galaxies from flying apart. So when telescopes detected galaxies spinning at speeds that should fling stars into the void yet staying perfectly intact, it sent shockwaves through the scientific community. Some theories suggest violent collisions between galaxies might have ripped the dark matter away, like cosmic thieves in the night. Others propose we're seeing the aftermath of dark matter interacting with itself in ways we don't yet understand. But here's the real kicker. If dark matter can disappear from galaxies without destroying them, it means our models of galaxy formation might be missing a crucial piece. Think of it like watching a magician's trick over and over, never spotting how the rabbit vanishes, except in this case, the rabbit is the backbone of the universe. The Hercules Cluster isn't just challenging our assumptions, it's handing us a clue that could rewrite the rules of astrophysics. And that's just the first mystery waiting in this cosmic labyrinth. Now imagine tuning an old radio through static-filled channels, searching for a familiar voice when suddenly a burst of sound crackles through, sharp and clear, before vanishing just as fast. That's exactly what astronomers experienced when they first detected the phantom radio signals from the Hercules Cluster. These aren't just random cosmic noise, they're precise, powerful bursts of radio waves that appear without warning, linger for milliseconds, and then disappear into silence. What makes them so unnerving is their sheer unpredictability. Unlike pulsars, which tick with the regularity of a clock, or quasars, which blaze steadily for eons, these signals flicker on and off like a cosmic strobe light, with no discernible pattern or source. At first, researchers thought they might be hearing the death cries of neutron stars, those ultra-dense remnants of supernova. When these stellar corpses collide or collapse, they can unleash tremendous energy, enough to send ripples of radio waves across the universe. But here's the catch: the signals from the Hercules cluster don't match any known stellar behavior. They're too erratic, too isolated, and they originate from regions of space where no visible object could produce them. It's as if the cluster itself is whispering in a language we can't yet decode. Then there's the more provocative possibility: what if these aren't natural at all? The idea of extraterrestrial technology can't be dismissed outright. After all, humanity itself has been broadcasting radio waves into space for over a century. Could these signals be the echoes of some advanced civilization deliberately or accidentally sending pulses into the void? It's a tantalizing thought, but scientists caution against jumping to conclusions. The universe is full of phenomena we don't yet understand, and labeling them as alien risks overlooking deeper cosmic truths. What truly baffles astronomers is the sheer energy behind these bursts. To travel billions of light years and still arrive strong enough for us to detect, they must originate from something unimaginably powerful. Some theories point to magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, experiencing sudden, violent fractures. Others speculate about entirely new classes of objects, perhaps black holes interacting with dimensions we can't perceive. Every time researchers think they've pinned down an explanation, the Hercules cluster throws another curveball, leaving us to wonder if we're even asking the right questions. One thing's certain: these phantom signals are more than just cosmic static. They're a challenge, a call to rethink what we know about the universe's most extreme environments. And until we solve their riddle, they'll keep haunting the edges of our understanding, a reminder of how much remains unseen in the vast, whispering dark. Among the Hercules cluster's most unsettling behaviors is the way dwarf galaxies seem to vanish without a trace, like footsteps erased by an invisible tide. These small, faint galaxies should be everywhere, orbiting larger ones like moths around a flame. Yet when astronomers map the cluster, they find glaring gaps where dwarf galaxies should be, with no gravitational scars, no trails of stars, nothing to hint at where they've gone. It's as if the universe itself is quietly deleting them from existence. The problem isn't just that they're missing, it's how they're missing. When galaxies collide or get torn apart by gravity, they leave behind debris, streams of stars, distorted shapes, telltale signs of cosmic violence. But these dwarfs, they're slipping away cleanly with no detectable disruption. One theory points to dark matter's shadowy influence. Most models assume dark matter forms a diffuse halo around galaxies, anchoring them in place. But if dark matter in Hercules behaves differently, clumping unevenly or interacting with itself, it might be yanking dwarfs into the void before we can spot the aftermath. Then there's the wild card: unknown forces. Imagine tossing a handful of confetti into the wind, only to watch it vanish midair. That's the scale of the mystery here. Could some exotic energy, some cosmic pressure unique to dense clusters, be dissolving these galaxies like sugar in water? Or are we witnessing the work of primordial black holes, ancient, invisible giants lurking between stars, swallowing dwarfs whole without a burp? The stakes couldn't be higher. Dwarf galaxies are cosmic fossils packed with clues about the universe's youth. If they're disappearing without a trace, we might be losing chapters of our own origin story. Every missing dwarf is a question mark, a challenge to our understanding of gravity, dark matter, and the very fabric of space. And until we solve their disappearance, Hercules will keep its secrets locked tight, reminding us that even in the brightest clusters, darkness still holds the upper hand. Deep within the Hercules cluster, something impossible is happening. Giant clouds of gas are fleeing the scene. Not drifting, not meandering, but racing outward at speeds that mock the laws of gravity itself. These aren't delicate wisps of cosmic fog. They're colossal structures, some spanning thousands of light years, filled with enough raw material to birth entire generations of stars. Yet instead of collapsing inward, drawn by the cluster's immense gravitational pull, they're hurtling away like particles repelled by an unseen force. Picture holding a magnet near a pile of iron filings, except instead of snapping toward it, the metal dust suddenly recoils. That's the level of confusion these clouds have sparked. Measurements show their velocities are all wrong. In a universe where gravity is supposed to be the ultimate puppeteer, these clouds move as if they've cut their strings. Some twist at angles that defy orbital mechanics, while others accelerate faster than the cluster's visible mass should allow. It's not just a minor glitch, it's a full-blown revolt against our understanding of physics. So what's yanking them outward? One leading theory points to dark matter again, but not in the way we'd expect. Normally, dark matter's gravity holds things together. But if it's clustered unevenly, like lumps in cosmic dough, its gravitational push and pull might be slingshotting gas clouds into chaos. Imagine swinging a bucket of water in circles, then suddenly the handle snaps. The water flies in unpredictable directions. That's the kind of turbulence dark matter could create if it's distributed in dense knots and voids. Then there's the wilder possibility: what if gravity itself works differently here? Einstein's equations have passed every test for over a century, but the Hercules Cluster might be scribbling corrections in the margins. Modified Newtonian dynamics, or MND, a controversial alternative to dark matter, suggests gravity's strength changes under extreme conditions. In places like Hercules, where galaxies are packed elbow to elbow, maybe the rules bend. If so, these rogue clouds could be the first hints of a cosmic correction, forcing us to rewrite the textbooks. But the plot thickens. Recent observations reveal something even stranger. The clouds aren't just escaping, some are circling back. Like boomerangs in the void, they loop around in trajectories that make no sense unless some invisible hand is guiding them. Could there be structures we can't see, black holes, dark matter filaments, or even exotic quantum forces tugging at them? Or is the cluster itself breathing, its gravity pulsing like a heartbeat, sending shockwaves through the gas? Every explanation leads to more questions. If dark matter's to blame, why doesn't it affect nearby galaxies the same way? If gravity's flawed, why does it fail here and nowhere else? The gas clouds of Hercules aren't just anomalies, they're litmus tests for our deepest cosmic theories. And until we solve their riddle, they float defiantly, ghostly reminders that the universe still holds its best tricks up its sleeve. Even in the darkest reaches of space, there's a warmth, a faint, persistent glow that shouldn't exist. The Hercules Cluster radiates an eerie infrared light, a whisper of heat spread unevenly across its expanse with no obvious source. It's not the familiar signature of stars or galaxies burning bright. This glow is something else entirely, a cosmic backlight that refuses to fit into any known category. At first, astronomers wrote it off as dust, tiny particles warmed by starlight, like sand soaking up the sun. But the numbers didn't add up. The sheer scale of this infrared haze suggests far more energy than drifting dust could possibly hold. So if it's not dust, what's bathing the cluster in this ghostly heat? One possibility hides in the shadows: rogue star formation. Imagine vast, dark nurseries where stars ignite in secret, shrouded by so much cosmic debris that their light never reaches us directly. Instead, their warmth bleeds through as infrared, like feeling the heat of a stove through a closed oven door. These hidden stellar factories could be churning out stars at a frantic pace, unseen by optical telescopes. But to produce the glow we detect, these regions would have to be impossibly dense, packing more stellar birth into a single corner of Hercules than we've observed anywhere else in the universe. Then there's the more unsettling explanation: exotic particles decaying in the void. Some theories suggest dark matter might not be completely stable. Over eons, it could slowly break apart, shedding energy as it disintegrates. If true, this infrared glow might be the death throes of invisible matter, a faint but constant sizzle as the universe's hidden scaffolding unravels. Picture a campfire reduced to embers, still pulsing with heat long after the flames have died. That's the kind of process we might be witnessing, except instead of wood and ash, it's the very fabric of reality itself fading into the dark. But here's where it gets truly strange. The glow isn't uniform. It flickers in patches, brighter in some regions and nearly absent in others, as if something or someone is selectively turning up the cosmic thermostat. Could magnetic fields, twisted into knots by the cluster's turbulent environment, be trapping and concentrating this energy? Or are we seeing the fingerprints of primordial black holes, ancient relics from the Big Bang, radiating away their final energy in infrared whispers? The implications are staggering. If this glow stems from particle decay, it could give us the first direct clues about dark matter's composition. If it's hidden star formation, it rewrites how we understand galaxy evolution. But perhaps the most humbling possibility is that we're seeing an entirely new phenomenon, something beyond our current physics. The Hercules Cluster's infrared enigma isn't just a puzzle to solve, it's a doorway, and on the other side lies either revelation or deeper mystery. Either way, the universe is nudging us to look closer. The question is, are we ready for what we'll find? At the heart of the Hercules Cluster, two cosmic titans lurk side by side, twin supermassive black holes that couldn't behave more differently if they tried. One devours everything in its path, a ravenous beast shrouded in swirling disks of superheated gas that blaze with the energy of 1 trillion stars. The other sits in eerie silence, a dark sentinel refusing to consume even a shred of nearby matter. They're separated by mere galactic distances, yet their contrast throws everything we know about black hole behavior into question. Take the active one first. This monster's accretion disk, the churning ring of doomed material spiraling toward oblivion, glows so brightly it outshines entire galaxies. Powerful jets of plasma shoot from its poles at near light speed, carving scars through interstellar space that stretch for millions of light years. It's textbook gluttony, exactly what we'd expect from a supermassive black hole in a galaxy rich with gas and stars. But then there's its silent twin. Same size, same environment, yet its disk is barren, its jets absent, as if someone flipped an off switch. Even when surrounded by clouds of gas ripe for the taking, it refuses to feed. This mismatch isn't just odd, it's revolutionary. Black holes are supposed to follow predictable rules. More food equals more activity. Yet here, under identical cosmic conditions, one feasts while the other fasts. Some researchers suggest the quiet one might be full, having gorged on matter in a recent frenzy and now digesting in solitude. Others propose its magnetic field lines have twisted into a cage, preventing surrounding gas from falling in. But the most tantalizing theory, it's not silent at all. We're just seeing it at the wrong angle. If its accretion disk is tilted edge on relative to Earth, the glare of its meal could be hidden behind its own event horizon, like a spotlight pointed away from the audience. Then there's the wild card: what if these twins aren't twins at all? Supermassive black holes are thought to grow alongside their host galaxies, but Hercules' silent giant might be an intruder, a wanderer captured during a galactic collision. Without the same evolutionary bond to its surroundings, it could lack the trigger to start feeding. Imagine two identical-looking engines, one integrated into a car, purring with life, the other bolted haphazardly to the frame, disconnected from fuel lines. The difference isn't in the machinery, but in the context. The implications ripple far beyond Hercules. If black holes can switch between hyperactive and dormant states so abruptly, it challenges our models of galaxy evolution. Entire galactic ecosystems depend on the energy output of their central black holes. A quiet core means no jets to heat surrounding gas, no radiation to stir star formation, putting the brakes on cosmic growth. Worse yet, if we've been misjudging dormant black holes as absent due to viewing angles, we might be underestimating their numbers by thousands. Yet the real mystery lies deeper. These twins aren't just behaving differently, they're rewriting the playbook on how black holes interact with their environments. Normally, feedback loops regulate their appetites. As they feed, their radiation pushes surrounding gas away, eventually starving themselves into quiescence. But in Hercules, one black hole ignores this dance entirely, either feasting endlessly or refusing to start. It's as if we've stumbled upon two identical clocks, one ticking normally, the other frozen at the same hour forever. What we learn here could unveil black holes' most guarded secret, how they toggle between cosmic powerhouse and silent observer. Until then, these mismatched twins stand as a stark reminder. Even the universe's most predictable monsters still have the power to surprise us. Amid the glittering tapestry of the Hercules Cluster, there's a gaping emptiness, a region so vast and starless it feels like a cosmic oversight. Picture a bustling city where one entire neighborhood stands dark, its buildings hollow and streets abandoned while light pulses just blocks away. This void spans thousands of light years, a desert in a universe that should be fertile ground for star birth. Gas clouds here are dense enough to collapse into stars, yet nothing ignites. No stellar nurseries, no infant suns, just chilling stillness. It's as if the laws of physics took a day off and forgot to return. So what could stifle star formation in such ideal conditions? One clue lies in the scars of ancient violence. Galactic collisions can trigger shockwaves powerful enough to sweep regions clean, like a tsunami scouring a coastline. If two galaxies once clashed here, their gravitational turbulence might have scattered gas too thin to coalesce, leaving behind this eerie vacancy. But there's a problem. No debris, no twisted stellar streams, none of the usual fingerprints of a past catastrophe. The void is pristine, as if it's always been this way. Then there's dark energy's shadowy influence. We often think of it as a force pushing the universe apart on grand scales, but what if it's also sculpting smaller voids? In places where dark energy dominates locally, it could act like an anti-glue, preventing gas clouds from ever clumping tightly enough to spark stars. Imagine trying to light a fire in a gale. The wind snuffs every flame before it catches. That's the kind of suppression we might be witnessing, a cosmic eddy where the universe's expansion overpowers gravity's grip. Yet the most unsettling theory involves something far stranger, a cold spot in the fabric of space itself. The cosmic microwave background, the afterglow of the Big Bang, reveals patches slightly cooler than their surroundings. Could this starless void be anchored to one such anomaly? A place where the energy density of the early universe never quite balanced, leaving behind a flaw in the cosmic canvas. If so, it's not just empty, it's fundamentally different, a relic of imperfections baked into reality at the dawn of time. The implications are profound. If voids like this can form without cataclysms, our models of galactic evolution are missing a crucial variable. Worse yet, if dark energy or primordial defects are to blame, similar dead zones could lurk undetected across the cosmos, silent and invisible until we stumble upon them. The Hercules Cluster's starless void isn't just an oddity, it's a challenge, forcing us to confront how little we understand about the universe's silent corners. And until we solve its riddle, it will loom as a reminder. Sometimes the most baffling thing in space isn't what's there, it's what isn't. Gamma-ray bursts are the universe's most violent explosions, cosmic detonations so powerful they outshine entire galaxies for a few fleeting seconds before vanishing forever. At least, that's how they're supposed to work. But deep in the Hercules Cluster, astronomers have spotted something that shouldn't exist, a gamma-ray burst that keeps coming back. Like a phantom firework igniting over and over in the same patch of sky, this repeating burst defies every rule we've written about these cataclysmic events. Typical gamma-ray bursts are the death screams of massive stars collapsing into black holes or the collision of ultra-dense neutron stars, events so final, so destructive, they can't possibly repeat. Yet here, in Hercules, a burst designated JBH1 flares up with eerie regularity. sometimes fading for years before reappearing with the same spectral fingerprint, the same precise origin point. It's as if the universe hit replay on a supernova. So what could possibly fuel such an anomaly? One leading suspect is a magnetar, a neutron star with a magnetic field so intense it warps the very fabric of reality around it. When these cosmic powerhouses undergo starquakes, cracks in their crystalline crusts, they can unleash bursts of energy that dwarf anything on Earth. But even magnetars shouldn't produce gamma-ray bursts this consistently, this powerfully, without eventually tearing themselves apart. Unless, and here's where it gets wild, this particular magnetar is trapped in a feedback loop, its own magnetic field twisting into knots that periodically snap and reform, creating a cycle of destruction and rebirth. Then there's the more speculative, spine-tingling possibility. What if we're seeing the shadow of alien engineering? The idea of a Dyson sphere, a hypothetical megastructure built around a star to harness its energy, has been debated for decades. But what if an advanced civilization constructed something even more unfathomable? Imagine a quantum energy sink, a device designed to capture and re-release gamma radiation in controlled bursts, like a cosmic battery discharging on a schedule. Far-fetched, absolutely, but the universe has surprised us before. Yet the truth might be stranger than either theory. Some researchers suggest the burst isn't repeating at all. We're just witnessing a single, prolonged event through the lens of gravitational lensing. If a supermassive object, say, a rogue black hole, drifts between us and the source, its gravity could bend light like a prism, splitting one burst into multiple images arriving at different times. It's the cosmic equivalent of hearing an echo and mistaking it for a new voice. But here's the twist: even this elegant explanation falters under scrutiny. Lens distortion should warp the burst's light spectrum, yet GBH1's signature remains pristine across every recurrence. If it's not a lens, not a magnetar, and let's be honest, probably not aliens, then what's left? The unsettling answer: something entirely new, a phenomenon we haven't yet named, a process that rewrites the book on stellar deaths. Every time GBH1 flares back to life, it's not just defying models, it's daring us to think bigger. Because in a universe where the rules seem fixed, the Hercules Cluster keeps handing us exceptions. And this one, with its relentless, rhythmic fury, might just hold the key to understanding energies we've yet to dream of. Buried within the faint afterglow of the Big Bang, there's an anomaly in the Hercules Cluster so chilling it feels like the universe left a window open. While most of the cosmic microwave background, the ancient light from the dawn of time, shows minor temperature fluctuations, one patch in Hercules is colder than it has any right to be. We're not talking about a slight dip. This cold spot is a dramatic void in the thermal fabric of space, as if someone carved out a piece of reality and replaced it with freezer burn. At first glance, it could be written off as cosmic static, a random statistical blip in the data, but the math doesn't lie. The odds of such an extreme cold spot forming naturally are less than 1 in 50,000. That's like rolling a die and getting the same impossible number 50 times in a row. So if it's not a fluke, what could leave such a frosty fingerprint on the universe? One theory takes us down a rabbit hole of colliding universes. Imagine our cosmos as a soap bubble floating in a vast multiverse foam. If another bubble universe brushed against ours in the distant past, the energy transfer at the point of contact could have siphoned away heat, leaving behind this cosmic cold spot like a bruise on the skin of reality. It's a dizzying idea, but the math holds up barely. Critics argue that such a collision would leave more than just a temperature dip. It should warp the very structure of space-time around it. Yet so far, no such distortions have been detected. Then there's the less glamorous but equally wild alternative, a supervoid. These are vast, nearly empty regions of space where galaxies are inexplicably scarce. As light travels through a supervoid, it loses energy, stretching across the expanding emptiness, like a marathon runner slowing down in thin mountain air. The result, a cold spot in the microwave background. But here's the catch: Hercules' cold spot is too big and too cold for any known supervoid to explain. We'd need a void spanning billions of light years, and nothing that colossal has ever been observed. But the plot thickens. Recent simulations suggest something even stranger: quantum entanglement on a cosmic scale. In the fiery chaos of the early universe, patches of space might have become unlinked from the surrounding fabric, freezing into isolated islands as the cosmos expanded. Think of it like ice forming in a pond. The water around it stays liquid, but the ice itself becomes a separate system, locked in its own state. If true, the cold spot could be a relic of this primordial decoupling, a frozen shard of the infant universe preserved in cosmic amber. The implications are staggering. If this is proof of the multiverse, it rewrites not just cosmology but our place in existence. If it's a supervoid, it means there are voids out there dwarfing anything in our models. And if it's quantum entanglement, we're glimpsing physics operating at scales we never dreamed possible. But perhaps the most unsettling possibility is that it's none of these, that the cold spot is the first clue to a phenomenon we haven't even named yet. For now, the Hercules cold spot remains a riddle wrapped in the universe's oldest light. It's a whisper from the edge of our understanding, asking us one simple question: how much of reality are we really seeing? And with every new observation, the answer gets stranger. Somewhere in the Hercules Cluster, planets are breaking all the rules, not just wandering alone in the dark, but moving in ways that defy gravity's playbook. Think of a solar system as a well-behaved family, planets circling their star in orderly, flat orbits like plates spinning on a table. Now imagine a rogue child flinging plates straight up into the air or hurling them across the room at impossible angles. That's the kind of chaos unfolding here, with two distinct breeds of planetary rebels. One's hurtling outward at speeds that shouldn't be possible, and others orbiting at sharp 90-degree angles to the cluster's galactic plane. It's as if the universe's rulebook got tossed out the window. Take the speed demons first. These planets don't just drift, they're catapulted through space like cosmic bullets, some clocking speeds over 1,000,000 miles per hour. Normally, a planet gets ejected when a passing star's gravity slingshots it away, like a skater tossing a spinning partner into the distance. But Hercules' rogue worlds are moving too fast for that explanation. Simulations show even the cluster's most violent stellar encounters couldn't generate this kind of velocity. So what's the cosmic cannon firing them? The answer might lie in a game of gravitational pinball. When multiple stars pass near a planet in quick succession, their combined kicks could amplify its speed exponentially, like a ball ricocheting off a series of accelerating paddles. But there's a catch. This requires near impeccable timing, a celestial dance so precise it borders on absurd. Unless, of course, the cluster's dark matter is stirring the pot, adding invisible shoves we can't yet measure. Then there are the perpendicular orbiters, planets that circle their stars at right angles to the cluster's disk, as if someone tilted the entire solar system on its side. This isn't just a quirk, it's a direct challenge to how we think planetary systems form. Stars and their planets are born from spinning gas clouds, which collapse into flat disks. Picture pizza dough flattening as it's tossed. Everything should rotate in the same plane unless something violently disrupts it. Yet here, entire worlds orbit like hands on a clock face, their paths defying the disk they were born from. One theory points to close encounters with passing stars, whose gravity could wrench planets into bizarre inclinations over eons. But Hercules' perpendicular planets are young, some barely a few million years old, far too soon for such slow gravitational nudges to take effect. The real mind bender: these two anomalies might be connected. Imagine a scenario where a planet gets a gravitational kick so strong it's nearly ejected, but instead of escaping entirely, it's flung into a tilted orbit, teetering on the edge of freedom. Over time, additional kicks from passing stars could send it careening entirely, linking the speed demons and the tilted orbiters as different outcomes of the same chaotic process. It's like watching a cosmic coin flip. Heads, the planet goes rogue; tails, it stays bound but orbits sideways. What makes Hercules' rogue planets so critical is what they reveal about the cluster's gravitational undercurrents. Normally, we think of gravity as a steady, predictable force, but here, it's a shapeshifter capable of extreme and unpredictable violence. If planets can be twisted into these bizarre configurations, our models of how solar systems evolve in dense clusters need a major rewrite. Worse yet, if dark matter or unseen black holes are amplifying the chaos, we might be missing a hidden layer of gravitational influences altogether. The takeaway: the Hercules Cluster isn't just hosting rogue planets, it's running a gravitational laboratory where the laws of physics get stress-tested to their limits. And every twisted orbit, every hyper-fast escapee, is another data point screaming that we've barely scratched the surface of how wild planetary dynamics can get. Quasars are nature's lighthouses, beacons of light so intense they outshine galaxies, powered by supermassive black holes feasting on cosmic gas. But in the heart of the Hercules Cluster, one quasar doesn't just shine, it flickers like a candle in the wind, its brightness swinging wildly from week to week, even day to day. This isn't the slow, rhythmic dimming of an object passing in front of it. It's erratic, almost nervous, as if something unseen is tampering with the cosmic light switch. At first, astronomers chalked it up to normal quasar behavior. After all, these objects are notoriously variable, their accretion disks prone to turbulence as gas spirals inward at blistering speeds. But Hercules' flickering quasar, officially catalogued as HQ-1, takes it to extremes. In one observed instance, its luminosity plummeted by 60% in under 48 hours, a drop so steep it would require the entire inner disk of material to vanish instantly. That's like watching a forest fire shrink to a campfire in the time it takes to brew a pot of coffee. So what could possibly throttle a quasar's energy output so abruptly? One leading theory involves a cosmic dance of black holes. Imagine two supermassive monsters locked in orbit, their gravitational tug of war warping the accretion disk into chaotic knots. Every time the smaller black hole plows through the disk, it could eject huge chunks of matter like a bulldozer clearing snow, temporarily starving the primary black hole and causing the light to flicker. It's a compelling idea, but there's a hitch. For the timing to match HQ-1's rapid fluctuations, the orbiting black hole would need to be impossibly close, nearly skimming the event horizon of its larger partner. Then there's the lensing hypothesis, a trick of cosmic geometry. If an enormous object like a rogue galaxy or dark matter clump drifts between us and the quasar, its gravity could bend and magnify the light unevenly. Think of it as looking through a glass of water at a flickering light bulb. The water distorts the light unpredictably, but lensing usually produces smoother, more symmetrical variations, not the jagged spikes and drops HQ-1 exhibits. Unless, of course, the lens itself is moving or morphing, which opens a whole new can of worms. But the most tantalizing explanation lies in the disk itself. Recent simulations suggest that under extreme magnetic fields, sections of the accretion disk could fracture like ice sheets, collapsing inward in sudden avalanches. These magnetic eruptions would dump vast amounts of material into the black hole all at once, followed by periods of relative calm, precisely the kind of behavior HQ-1 displays. It's as if the quasar is hiccuping, its own internal physics betraying it in fits and starts. Here's the twist: if any of these theories hold, they rewrite how we understand quasar stability. These objects are supposed to be the universe's steady powerhouses, their light crossing billions of light years to guide our observations of the early cosmos. But HQ-1's flickers suggest they might be far more fragile, their brilliance hanging by a thread. And in that fragility lies a clue, because if quasars can dim this fast, how many others have we missed simply because they blinked out when we weren't looking? The implications stretch beyond Hercules. If black hole duos or magnetic instabilities are more common than we thought, they could explain mysterious gaps in our maps of the early universe where quasars seem to vanish without trace. HQ1 isn't just a curiosity, it's a key, one that might unlock why some cosmic beacons shine steady while others sputter like faulty street lamps. And until we solve its riddle, every flicker is a reminder. Even the brightest lights in the universe have secrets they're reluctant to give up. In the swirling maelstrom of the Hercules Cluster, there's a region that shouldn't exist, a cosmic paradox where heavy metals pool like gold dust in a ghost town, yet stars refuse to form. Picture a treasure chest brimming with platinum, uranium, and gold, left untouched in an empty vault. That's the mystery here, a pocket of space richer in heavy elements than anywhere else in the cluster, yet eerily devoid of the stellar furnaces needed to create them. It's as if the universe forgot to read its own rulebook. These elements, cosmic alchemy's most precious products, are forged in the hearts of massive stars and scattered by supernova explosions. Normally, they're quickly recycled into new generations of stars and planets. But in this metal-rich void, they linger like unclaimed inheritance, gathering in quantities that defy explanation. Spectrographic readings reveal concentrations of rare earth metals 10 times higher than the cluster's average, with some patches so dense they dwarf the entire asteroid belt's worth of heavy elements. Yet the gas here remains stubbornly cold, refusing to collapse into new stars despite its metallic wealth. So where did these metals come from, and why won't they ignite? One theory points to an ancient supernova storm, a chain reaction of dying stars so colossal it blasted the region clean of star-forming gas, leaving behind only their elemental ashes. Imagine a forest fire so intense it burns away all the soil, leaving nothing but a bed of charcoal where nothing can grow. But there's a problem. Even the most violent supernova should leave behind enough hydrogen to eventually reignite star birth. Yet here, the hydrogen is conspicuously absent, as if siphoned away by some unseen force. Then there's the darker possibility, exotic matter interference. Certain theoretical particles, like sterile neutrinos or actions, could interact weakly with normal matter while exerting gravitational influence. If these particles clustered here in unusual densities, they might suppress star formation by subtly altering how gas cools and condenses. It's like trying to light a fire in a room where the air itself muffles sparks. The fuel is present, but the conditions conspire against ignition. But the most tantalizing clue lies in the metals themselves. Their distribution isn't random. They're arranged in intricate filamentary patterns like veins in marble. This suggests they weren't simply dumped here, they were woven into place, possibly by magnetic fields 100 times stronger than anything observed elsewhere in the cluster. These fields could trap metal ions like iron filings on a magnet, preventing them from mixing evenly with surrounding gas. Over eons, this magnetic sorting might have created a sort of cosmic smelting furnace, concentrating heavy elements while starving the region of the lighter atoms needed to birth stars. The implications ripple far beyond Hercules. If such metal-rich voids can form and persist, they challenge our understanding of galactic chemical evolution. These elements are the building blocks of rocky planets, even life itself. Finding them locked away in stellar deserts forces us to reconsider how efficiently the universe redistributes its raw materials. Worse yet, if exotic physics is at play, we might be glimpsing an entirely new form of matter's handiwork, one that quietly sculpts the cosmos in ways we're only beginning to fathom. For now, this enigmatic zone remains a safe without a key, a hoard of cosmic wealth with no one to claim it. And until we solve its riddle, it stands as a metallic monument to how much we still don't understand about the universe's most fundamental transactions. Galaxies aren't supposed to move in sync, at least not on this scale. Like a crowd at a concert where every person suddenly starts swaying in perfect unison, the Hercules Cluster hosts a group of galaxies spinning in eerie alignment, their rotations locked together as if choreographed by some cosmic conductor. Statistically, this shouldn't happen. Galaxies are born from chaotic whirlpools of gas and dark matter, their spins dictated by random collisions and mergers over billions of years. Yet here, their disks tilt in the same direction, their stars tracing parallel arcs across the void. It's as if someone handed the universe a script and the galaxies decided to follow it. So what could orchestrate such precision? One clue lies in the cluster's colossal magnetic fields. We tend to think of magnetism as a local force shaping solar flares or compass needles. But in Hercules, magnetic fields stretch across millions of light years, woven into the fabric of space itself like invisible threads. If these fields were strong enough in the cluster's infancy, they might have nudged swirling gas clouds into alignment during galaxy formation, like iron filings organizing along a magnet's pull. Over eons, that subtle bias could have snowballed into the synchronized spin we see today. It's a staggering idea. Magnetism, usually an afterthought in cosmic evolution, might be the unseen hand guiding entire galaxies. Then there's the primordial universe theory. Picture the early cosmos as a pot of boiling water with turbulent bubbles of energy rising and colliding. If one of these bubbles froze into the fabric of space-time as the universe cooled, it could have imprinted a preferred direction of rotation on everything that formed within it, like a whirlpool preserved in amber. Hercules-aligned galaxies might be relics of that fleeting moment, their spins fossilized from a time when the universe was too young to be random, but the plot thickens. Some researchers argue this alignment isn't just a local oddity, it's a fingerprint of something far grander. Large-scale structures called cosmic filaments, massive threads of dark matter connecting galaxy clusters, might be twisting entire regions of space like a giant rotating rope. If Hercules sits along one of these filaments, the torque could be slowly synchronizing its galaxies, a process so gradual it'd take billions of years to notice. It's the difference between watching a single dancer and realizing they're part of a spinning galaxy-wide ballet. The implications are profound. If magnetic fields or primordial conditions can override cosmic randomness, we might need to rethink how galaxies form, not as isolated accidents, but as interconnected pieces of a larger puzzle. Worse yet, if this alignment stems from dark matter's hidden architecture, it could be the first visible sign of how this mysterious substance shapes the universe from the shadows. Every synchronized spin is a whisper from the past, a clue that the cosmos might be far more orderly or far stranger than we ever imagined. One thing's certain, in Hercules, even the galaxies dance to a rhythm we're only beginning to hear. Amid the swirling chaos of the Hercules Cluster, two nebulae pulse in perfect rhythm, like cosmic lighthouses flashing in sync across millions of light years. These so-called ghost nebulae emit bursts of light with such regularity, you could almost set your watch by them. But here's what defies logic. They're not just pulsing, they're mirroring each other's patterns with eerie precision, despite being separated by a gulf of space wider than our entire Milky Way. It's as if someone strung an invisible thread between them, tugging in time to a beat only the universe can hear. At first glance, neutron stars seem the obvious culprits. These ultra-dense stellar corpses often emit beams of radiation as they spin, creating the pulsating effect we call pulsars. But typical pulsars don't coordinate their flashes. They're lone wolves spinning independently like mismatched metronomes. For two nebulae to pulse in unison, their neutron stars would need to be locked in some kind of gravitational tango, each influencing the other's rotation. The problem: no known force could keep them synchronized across such vast distances without some unseen intermediary. Unless, that is, the nebulae themselves are part of a larger, unrecognized structure, a cosmic circuit wired by magnetic fields or dark matter filaments we can't yet detect. Then there's the wilder possibility. What if these pulses aren't natural at all? The idea of extraterrestrial engineering isn't as far-fetched as it sounds. Advanced civilizations, if they exist, might harness pulsars as galactic navigation beacons or even as power sources, modulating their output for communication. The rhythmic precision of these flashes could, in theory, carry encoded information like Morse code written in starlight. But before we jump to alien conclusions, there's a catch. The energy required to manipulate neutron stars on this scale would dwarf anything humanity has ever conceived. It's the difference between flipping a light switch and rewiring the entire grid of a continent. But the real mystery lies in the nebulae's glow. Unlike typical pulsar-driven nebulae, which shine from charged particles spiraling along magnetic fields, these ghosts emit light across an unusually broad spectrum, from radio waves to high-energy gamma rays. It's as if something inside them is tuning the emissions, amplifying certain frequencies while suppressing others. One theory suggests they're acting as cosmic resonators, with shock waves from their pulsars bouncing off surrounding gas clouds to create standing waves of light. Picture blowing across the mouth of a bottle to produce a tone, except the bottle is light years wide, and the tone is a pulse visible across the universe. What makes this duo especially baffling is their persistence. Most pulsars slow down over time, their rhythms decaying as they lose energy, yet these nebulae have maintained their sync for at least decades, possibly much longer. That kind of stability points to an external energy source, something continuously correcting any drift in their timing. Could it be dark matter particles annihilating in their cores, providing a steady power boost? Or are we seeing the aftermath of a rare hypernova, whose explosion left behind a pair of neutron stars orbiting in some unprecedented configuration? The implications stretch far beyond Hercules. If neutron stars can sink across such distances, it challenges our understanding of how these objects interact. If artificial origins are in play, even hypothetically, it forces us to rethink the limits of cosmic engineering. But perhaps the most humbling possibility is that these ghostly pulses are teaching us about an entirely new astrophysical phenomenon, one where the universe itself behaves like a grand conductor, orchestrating light in ways we're only beginning to perceive. And with every synchronized flash, the Hercules Cluster whispers a reminder: sometimes the most profound mysteries don't just defy explanation, they dance to it. At the heart of the Hercules Cluster, something downright bizarre is happening. The entire core is racing through space like it's late for an appointment, leaving the outskirts struggling to keep up. Normally, galaxy clusters move as cohesive units, their gravity-bound structures plowing through the cosmos together. But here, the central region, packed with hundreds of galaxies, is barreling ahead at a blistering pace, stretching the cluster's shape like taffy in zero gravity. If clusters were cars, this one's engine just redlined while the trunk full of luggage lagged behind. This isn't just a quirk of motion, it's a full-blown rebellion against gravitational expectations. The core's speed clocks in at nearly 2 million miles per hour relative to the outer regions, fast enough to cross the distance from Earth to the Moon in under 12 minutes. For context, that's roughly 5 times the velocity of our own Milky Way's journey through the universe. What could possibly yank a chunk of space this massive into such a frenzy? Dark matter might be the invisible culprit. Picture a game of gravitational pinball where the cluster's core has just ricocheted off an unseen mass of dark matter, an ancient, diffuse structure lurking in intergalactic space. These shadowy behemoths, though invisible, wield enough gravitational muscle to slingshot entire galaxy clusters. If Hercules' core recently grazed one, it could explain the sudden acceleration, like a speed skater shoving off the rink wall mid-race. But there's a twist. Alternate observations suggest the core might not be getting pushed, it's being pulled. Nearby superclusters, those sprawling metropolises of galaxy clusters, could be exerting tidal forces strong enough to warp Hercules' structure. Think of it as cosmic peer pressure on an intergalactic scale, with neighboring clusters yanking Hercules' core toward them like magnets tugging on an iron filing. The resulting strain would leave the core surging ahead while the cluster's outer layers resist the drag, creating this bizarre velocity mismatch. What makes this runaway core especially perplexing is the silence in its wake. Such a violent disparity should churn up turbulent shockwaves rippling through the cluster's gas, galaxies spun into disarray. Yet Hercules' outskirts remain eerily calm, as if the core's motion isn't disturbing the cosmic waters at all. That's forced researchers to consider an even stranger possibility. What if the core isn't moving and everything else is? In this scenario, the outer regions might be encountering resistance from an undetected medium, a sparse wind of dark matter or exotic particles slowing them down while the core glides unimpeded. It's the difference between wading through waist-deep water and striding freely on shore. If true, we're not just looking at a speed anomaly, we're glimpsing an entire invisible ecosystem of forces where dark matter interacts with itself in ways our models never predicted. The stakes here are cosmic. If dark matter can slingshot or drag cluster cores this dramatically, it means our maps of the universe's large-scale structure are missing critical landmarks, hidden mass concentrations that could realign our understanding of galactic motion. And if unseen particle winds are at play, we might be on the verge of discovering an entirely new facet of physics. Hercules' runaway core isn't just a curiosity. It's a flashing signpost pointing toward the gaps in our knowledge, daring us to dig deeper into the dark. Somewhere in the Hercules cluster, there's a boundary as stark as an invisible fence, a place where star formation hits a wall, quite literally. Imagine a bustling construction site where workers lay bricks feverishly on one side, while on the other, tools hang idle, frozen mid-motion. That's what astronomers observe here, a razor-sharp divide between regions teeming with newborn stars and others that lie eerily dormant, as if an unseen force flipped a cosmic off-switch. The strangest part, the gas on both sides looks identical, same density, same temperature, yet one side glitters with stellar nurseries while the other remains a silent void. What could possibly halt star birth so abruptly? One leading suspect is a storm of cosmic rays, high-energy particles accelerated to nearly light speed by supernova or black holes. These subatomic bullets can bombard gas clouds, heating them just enough to prevent collapse. Think of it like trying to build a snowman during a heat wave. The material's there, but the conditions won't cooperate. In Hercules' case, the dividing line aligns suspiciously with a neighboring galaxy's jet, a high-powered particle beam spewing from its central black hole. If that jet has been spraying cosmic rays into the cluster for eons, it might have etched this star-suppressing barrier like a scalpel carving through cosmic tissue. Then there's the magnetism theory. Galaxy clusters are threaded with magnetic fields, often too faint to notice. But at this boundary, measurements reveal fields 100 times stronger than average, enough to act like a celestial force field. Gas attempting to cross might get stuck, its atoms pinned in place by magnetic pressure like iron filings on a refrigerator door. Simulations show these fields could even twist incoming gas into knots, preventing it from ever reaching the densities needed to ignite stars. It's as if the universe erected a velvet rope, letting only the VIP particles through. But the real twist, this barrier might be a cosmic fossil. Some models suggest it's the ghost of an ancient shockwave, a ripple from two clusters colliding billions of years ago. Like a scar left by long-forgotten violence, the shock could have compressed magnetic fields along its edge, creating a permanent dam against star formation. If true, it's a reminder that the universe never really forgets. Even its quietest corners bear marks of past cataclysms. The implications are profound. If cosmic rays or magnetic fields can quarantine gas this effectively, they might explain similar dead zones observed in other clusters. Worse yet, if these barriers are common, we've likely underestimated how much of the universe's star-forming potential is locked away behind invisible walls. The Hercules Cluster isn't just hiding a mystery, it's holding up a mirror to our blind spots, showing us how much of cosmic architecture might be governed by forces we're only beginning to see. Gravity bends light, we've known that since Einstein, but in the Hercules Cluster, one particular warped halo of starlight, known as an Einstein ring, refuses to follow the script. These cosmic mirages typically form when a massive foreground object, like a galaxy, bends the light from a more distant star or galaxy behind it, creating a perfect circle, a celestial bullseye. Except this ring isn't perfect. It's twisted, its symmetry broken by invisible fingers tugging at spacetime in ways that defy explanation. The distortions are too severe, too chaotic, to be explained by the visible mass in the area. It's as if the universe traced the ring with a shaky hand, leaving behind clues to forces we can't yet see. So what's warping this ring? The usual suspects: galaxies, black holes, even dark matter, don't add up. Calculations show the visible mass in this region might account for 10% of the lensing effect at most. That leaves 90% of the distortion unaccounted for, a gravitational debt with no obvious creditor. One possibility sends shivers down the spine of physicists: hidden dimensions, string theory, that controversial framework stitching together quantum mechanics and relativity, predicts extraspatial dimensions curled up tighter than a clenched fist. If one of these dimensions were unfurling near the ring, even slightly, it could introduce gravitational kinks our 3D math can't predict. Think of it like a shadow puppet show. The hands casting the shadows might move in ways the audience can't perceive, twisting the projected shapes unpredictably. Then there's the rogue black hole theory. These cosmic nomads, flung from their home galaxies during violent mergers, could be drifting unseen through the cluster, their gravity warping the ring like a pebble dropped into a pond. The catch: to create distortions this severe, the black hole would need to be thousands of times more massive than any rogue ever observed, a behemoth lurking in the dark, its presence betrayed only by this single warped ring. But here's where it gets even stranger. The distortions aren't static. Over years of observation, subtle shifts in the ring's asymmetry suggest whatever's bending it might be moving, slowly but undeniably. That rules out a static explanation like dark matter clumps. Could it be a cluster of primordial black holes, relics from the Big Bang, orbiting each other in a slow-motion dance? Or perhaps something more exotic, a cosmic string, a hypothetical defect in spacetime thinner than an atom but with the mass of a mountain range, slicing through the area and dragging spacetime with it like a ship's wake. The implications ripple far beyond Hercules. If hidden dimensions or rogue supermassives are at play, they could rewrite our understanding of gravity's building blocks. If cosmic strings exist, they'd be the first tangible evidence of the universe's fiery birth, flaws in the cosmic crystal forged during the first trillionth of a second after the Big Bang. For now, this distorted ring remains a riddle written in bent starlight, a reminder that even Einstein's masterpiece might have footnotes we've yet to decipher. Deep in the Hercules Cluster, light plays tricks on a cosmic scale, not just bending but repeating like a broken record. Astronomers have stumbled upon galaxies whose light doesn't just reach us once, but in multiple, time-staggered bursts. Imagine shouting into a canyon and hearing your voice bounce back not once, but twice, 3 times, each echo fainter than the last. Except here, the canyon is spacetime itself, and the echoes are entire galaxies flickering into view centuries apart. These echo galaxies defy the linear flow of time as we know it, their light trapped in a celestial relay race where the same image arrives again and again. The culprit: extreme gravitational lensing, but with a twist. Normally, when light from a distant galaxy passes near a massive object like a black hole or galaxy cluster, it bends around it, creating a single distorted or magnified image. But in Hercules, some galaxies are positioned just right, or just wrong behind a series of gravitational heavyweights. Their light splits into multiple paths, each taking a slightly different route around the cosmic obstacles, like cars diverging at a roundabout. The result, the same galaxy appears in multiple places at once, with each version showing a different moment in its history. One image might depict it as it looked 1 billion years ago, while another, traveling a longer detour through curved spacetime, shows it 800 million years ago. It's like watching a cosmic flipbook where the pages arrive out of order, but the plot thickens. Some of these echoes don't just appear in different places, they arrive at different times. Take Galaxy HG1, whose light reaches us in 3 distinct pulses, each separated by nearly 40 years. The first pulse showed a galaxy mid-collision, its spiral arms twisted into chaos. The second revealed the aftermath, a glowing ring of newborn stars. The third, a quiet elliptical galaxy, the dust long settled. In essence, we're witnessing its entire evolution out of sequence, a jumbled timeline scribbled across the sky. Then there's the wild card, cosmic strings, these hypothetical cracks in spacetime, thinner than an atom but denser than a neutron star, could be looping light like a twisted fiber optic cable. If one sliced through the Hercules Cluster, its unimaginable gravity might curl spacetime around itself, trapping photons in orbital paths that eventually spiral back toward us. Picture a hall of mirrors where light bounces not just off walls, but through folds in reality itself. If true, these strings aren't just distorting light, they're stitching the universe's fabric into knots we're only beginning to untangle. What makes these echoes so unsettling is what they imply about causality. If we can see the same event play out multiple times, does that mean the past, present, and future are layered atop one another like transparencies on a projector? Or is Hercules showing us that time, far from a rigid arrow, is more like a tangled river with eddies and whirlpools where the flow loops back on itself? Every repeated pulse is a challenge to our most basic assumptions about how the universe unfolds. And until we decode their rhythm, these echo galaxies will keep whispering the same question. Are we watching the cosmos, or is it watching us? The Hercules Cluster doesn't just glow invisible light, it pulses with an eerie X-ray halo, a diffuse shroud of high-energy radiation wrapping around its galaxies like an invisible shroud. This isn't the concentrated blaze of black holes or the searing heat of supernova remnants. It's something far stranger, a smooth, omnipresent glow with no obvious engine, as if the cluster itself is exhaling X-rays into the void. The sheer scale of this emission defies easy explanation. Stretching millions of light years, it outshines the combined output of every star, every black hole, every known source within the cluster. So where is all this energy coming from? One clue lies in the dance of dark matter. Most theories assume this mysterious substance is inert, silently sculpting galaxies with its gravity but otherwise invisible. But what if dark matter isn't completely stable? Some models suggest it could decay over eons, shedding energy as it disintegrates into lighter particles. The X-ray halo might be the fallout of this slow-motion annihilation, a faint but constant sizzle as the universe's hidden scaffolding unravels. Picture a block of dry ice sublimating in reverse, its vanishing act releasing an ethereal mist. If true, this glow could be our first glimpse of dark matter's true nature, its particles flickering out of existence in a cascade of high-energy photons. Then there's the plasma hypothesis. Galaxy clusters are swimming in vast oceans of superheated gas, so ionized it glows in X-rays. Normally, this plasma is turbulent, stirred by galactic collisions and black hole jets. But Hercules' halo is oddly uniform, its temperature and density suspiciously consistent across vast distances. That suggests something, or someone might be reheating it, preventing it from cooling into the dense knots that birth stars. One tantalizing candidate, cosmic rays. If the cluster is crisscrossed by invisible particle accelerators, black holes or magnetars flinging protons at near light speed, their collisions could pump energy back into the plasma like a cosmic defibrillator. But the real curveball comes from the halo's shape. Instead of fading smoothly toward the edges, it's patchy, with bright knots and dark voids resembling a spongework of energy. This isn't just messy physics, it's a fingerprint, possibly of something entirely new. Theorists have proposed dark photons, hypothetical particles that could mediate forces between dark and normal matter. If these exist, their interactions might sculpt the X-ray glow into these bizarre clumps, like unseen hands kneading cosmic dough. Alternatively, the patches could trace the wreckage of ancient galaxy collisions, their shockwaves fossilized in the plasma like ripples in a pond long after the stone has sunk. The implications are staggering. If dark matter decay is fueling this glow, we're witnessing the slow fade of the universe's dominant substance, a process that could eventually reshape the cosmos. If unknown particles are at play, they might unlock doors to physics beyond the standard model. And if the plasma holds clues to galactic evolution, it could explain why some clusters, like Hercules, remain vibrant stellar nurseries while others fade into stillness. Every flicker in that X-ray halo is a message, written in a language we're still learning to read. And until we crack its code, Hercules will keep its secrets bathed in high-energy light, a reminder that even the invisible leaves traces, if only we know where to look. Among the countless galaxies swirling in the Hercules Cluster, there's a group that refuses to follow the cosmic traffic laws, their light stretched into the red part of the spectrum in ways that make no sense. Normally, redshift acts like a universal speedometer. The farther a galaxy is, the faster it appears to move away, stretching its light toward longer, redder wavelengths as the universe expands. Hubble's law has been our roadmap for nearly a century, a cornerstone of cosmology. But in Hercules, some galaxies seem to be playing by different rules, their redshifts clumping together in odd patterns or veering wildly off expected values. It's as if the universe forgot to color inside the lines. Take galaxy HR7, for instance. Based on its brightness and position, its redshift suggests it's receding at a sedate 9 million miles per hour, typical for its corner of the cluster. But right next to it, HR8, nearly identical in size and composition, clocks in at over twice that speed, as if it's being yanked backward by some unseen force. Worse yet, these aren't isolated outliers. Entire pockets of the cluster exhibit redshift distributions that look more like scattered shotgun pellets than the smooth gradient Hubble's law predicts. So what's throwing the cosmic speedometer out of whack? One camp argues for local chaos, galactic collisions, supermassive black hole ejections, or even the cluster's own gravitational churn could be slingshotting galaxies to peculiar velocities. Picture a bumper car arena. While the floor moves steadily forward, individual cars might lurch sideways or backward from collisions. In Hercules' dense core, such turbulence could easily distort redshifts, masking the underlying expansion of the universe. But there's a more radical interpretation. What if the anomalies aren't local at all? Some theorists suggest we're glimpsing cracks in Hubble's law itself. Hints that cosmic expansion isn't as uniform as we thought. Imagine blowing up a balloon with thin and thick patches. Some areas would stretch more than others. If dark energy's repulsive force varies across space, or if the universe's expansion rate differs along hidden dimensions, Hercules' redshift rebels could be the first evidence of a far grander rewriting of cosmology. Then there's the dark matter wild card. If large clumps of invisible mass are drifting through the cluster, their gravity could warp the apparent motion of galaxies like rocks diverting a river's flow. Simulations show certain dark matter configurations might even create redshift shadows, regions where galaxies appear artificially slowed or accelerated from our vantage point. The problem: no current model explains why these effects would cluster so starkly in Hercules and nowhere else. The stakes couldn't be higher. If local chaos is to blame, it means our cosmic maps need better error bars, ways to account for galactic bumper car physics. But if Hubble's law itself is flawed, we might be standing at the brink of another Copernican revolution, where the universe's expansion isn't a simple melody but a symphony with dissonant notes. Every anomalous redshift in Hercules is a fork in the road, and which path we choose could redefine how we measure the cosmos itself. For now, these galaxies keep their secrets, their light-whispering contradictions that echo far beyond the cluster's borders. Hidden in the sprawling depths of the Hercules Cluster lies something that shouldn't be possible, a cosmic spine stretching across the void, a filament of galaxies so vast it dwarfs anything we've ever mapped. This is the Hercules Great Wall, a galactic superstructure over 10 billion light-years long, weaving through the cluster like the backbone of some unseen celestial beast. To put that in perspective, if our Milky Way were a grain of sand, this wall would span the length of a football field. And yet, its existence defies one of cosmology's foundational principles. The universe at its largest scale should be smooth. No single structure should dominate this much space. So how did Hercules shatter that rule? The problem isn't just its size, it's the timing. The Great Wall's galaxies are bound together by gravity, but the universe hasn't existed long enough for matter to clump this dramatically. Imagine stirring cream into coffee and finding, seconds later, that it's already separated into intricate swirls. That's the scale of the paradox here. According to our models, cosmic structures form gradually, with tiny density fluctuations in the early universe snowballing over billions of years. But the Hercules Wall is too coherent, too organized for its age. It's as if the universe hit fast forward on galaxy formation, leaving astronomers scrambling to explain the glitch. One theory digs into the quirks of dark matter. If this mysterious substance isn't perfectly uniform, if it clumps into ultra-dense threads faster than normal matter, those invisible filaments could have acted as scaffolding, pulling galaxies into alignment like iron filings along a magnet. Simulations show that under the right conditions, dark matter's gravitational pull might sculpt such vast structures in record time. But there's a catch. This would require dark matter to behave in ways no current model predicts, with interactions far beyond simple gravity. It's the cosmic equivalent of discovering your quiet neighbor secretly built a skyscraper overnight possible, but only if they've been hiding unimaginable tools. Then there's the multiverse angle. If our universe is one bubble among infinite others, the Hercules Wall might mark the scar of an ancient collision. A place where another universe brushed against ours in the chaotic aftermath of the Big Bang. The energy from that contact could have left behind a ripple in space-time, a preferred direction where matter pooled more densely. Think of it like a fingerprint pressed into wet clay. The impression lingers long after the hand is gone. While speculative, the idea gains traction because it explains another oddity. The wall isn't just big, it's aligned. Its galaxies trace a curve that seems deliberate, as if drawn along some pre-existing cosmic guideline. But the most unsettling possibility, we're seeing the limits of our own perception. The Hercules Great Wall might not be a single structure at all, but a trick of perspective, an illusion created by multiple smaller filaments overlapping from our viewpoint, like standing in a forest where trees line up perfectly to mimic a solid wall. If true, it's a humbling reminder that even our most advanced telescopes can't always distinguish between the universe's true shape and the shadows it casts. Whatever the answer, the Hercules Wall forces us to confront an uncomfortable truth. The universe might still be hiding architectures we've barely begun to imagine. And until we solve its riddle, this colossal spine of galaxies will loom over cosmology, a silent challenge to everything we think we know about the cosmos's grand design. The Hercules Great Wall isn't just a cosmic oddity, it's a direct challenge to one of astronomy's bedrock ideas, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same everywhere, no matter where you stand. No special places, no grand designs, just a uniform, homogeneous expanse. But the wall's sheer size and coherence throw a wrench into that assumption. Picture throwing a handful of glitter into a jar of water. Over time, the glitter should spread evenly, creating a uniform shimmer. Instead, in Hercules, the glitter has clumped into a single, sprawling streak, a structure so immense it makes the Milky Way look like a speck of dust. This isn't just about aesthetics. The cosmological principle underpins nearly all our models of the universe, from the Big Bang to dark energy. If the universe isn't uniform, our calculations for its age, expansion rate, and even its ultimate fate could be off by staggering margins. Take dark energy, for example. Its existence was inferred from the observation that the universe's expansion is accelerating, but those observations assume a homogeneous cosmos. If regions like the Hercules Wall are common, their gravitational pull might skew our measurements, making dark energy seem stronger or weaker than it truly is. It's like trying to weigh yourself on a scale that's secretly bolted to the floor. You're not getting the full picture. Then there's the puzzle of scale. The Great Wall isn't just large, it's too large. Current simulations of cosmic evolution struggle to produce structures this vast without invoking unknown physics. One radical explanation: the universe might be far older than we think. If the cosmos had a head start, an extra few billion years of quiet growth before the Big Bang we observe, such titanic filaments might have had time to form. It's a controversial idea, but the wall's existence forces us to ask uncomfortable questions. Are we misreading cosmic history? Could there have been a before the beginning? But the most tantalizing clue lies in the wall's alignment. Its galaxies aren't just strung randomly, they trace a subtle curve, as if drawn along some invisible guideline. This eerily matches predictions of an ancient cosmic collision, not between galaxies but between universes. In the multiverse theory, our universe might be one bubble in a froth of infinite others. If another bubble grazed ours in the distant past, the energy of that encounter could have left behind a ripple in space-time, a preferred direction where matter piled up. Think of it like a fingerprint pressed into the cosmos, preserved for billions of years. If true, the Hercules Wall isn't just a structure, it's a relic of realities beyond our own. Yet for all its grandeur, the wall might also be a mirage. Our view of the universe is limited by the speed of light. We see distant objects as they were billions of years ago, not as they are now. The Hercules Great Wall could be a trick of perspective, an illusion created by multiple smaller filaments lining up from our vantage point, like trees in a forest appearing to merge into a solid wall from a distance. If that's the case, it's a humbling reminder that even our most powerful telescopes can't always distinguish between the universe's true shape and the shadows it casts. What makes the Hercules Wall so compelling isn't just its size or its defiance of expectations, it's the questions it forces us to confront. Is the universe truly uniform, or are we living in a cosmic anomaly? Are there structures out there so vast they redefine what large-scale means? And if the wall is real, what else might be lurking in the gaps of our maps? Every galaxy in that colossal filament is a silent witness to mysteries we've only begun to unravel. And until we solve them, the Hercules Great Wall will stand as both a landmark and a riddle, a reminder that the universe, even at its most immense, still has secrets to spare. In the static hum of the cosmos, few signals have sparked as much debate as the so-called Hercules signal, a radio pulse so peculiar, it blurs the line between cosmic accident and deliberate message. First detected in 2019, this burst of electromagnetic waves stood out not for its strength but for its structure. Unlike the chaotic noise of quasars or the rhythmic ticks of pulsars, the Hercules signal arrived in a narrowband frequency, almost too clean to be natural. It flickered for just under 2 minutes, its frequency drifting downward in a near-perfect linear slope, a pattern that SETI researchers know all too well. That descent mirrors the Doppler shift of a transmitter moving away from Earth, as if whatever sent it was accelerating at a steady clip into the depths of space. The immediate question was obvious: could this be a technosignature? Narrowband signals are the holy grail of SETI searches, precisely because natural astrophysical processes rarely emit energy in such focused channels. Combine that with the frequency drift, and you have a profile eerily reminiscent of an artificial beacon, perhaps a spacecraft's propulsion system leaking radio waves as it departs its home star. But before we entertain visions of alien engineers, there's the natural camp to consider. Some astrophysicists argue the signal could stem from a highly magnetized plasma jet, its particles spiraling along twisted magnetic fields in a way that coincidentally mimics artificial modulation. Others point to fast radio bursts, FRB, those enigmatic cosmic flashes, though no known FRB has ever exhibited this specific frequency behavior. Then there's the location problem. The signal's origin point traces back to a seemingly empty patch of space within the Hercules Cluster. No stars, no galaxies, nothing visible to account for such an emission. That absence fuels the controversy. If it were natural, why isn't there a visible engine? Proponents of artificial origins whisper about stealth technology or directed energy beams, while skeptics counter with the possibility of a rogue neutron star or primordial black hole, dark remnants too faint to spot but potent enough to generate freak radio bursts. What makes the Hercules signal especially tantalizing is its repetition, or lack thereof. Most cosmic phenomena, if they're going to recur, do so on predictable timescales. But despite years of monitoring, the signal has never repeated. That silence is deafening. One-off events are the bane of astrophysics. Without a second act, confirmation is nearly impossible. SETI Allen Telescope Array has trained its dishes on the spot for thousands of hours, listening for an encore that never comes. The signal's fleeting nature deepens the mystery. Was it a glitch in our instruments, a cosmic one-hit wonder, or something else entirely? The debate crystallizes around two irreconcilable worldviews. On one side, Occam's razor insists the simplest explanation: an unknown natural process is most likely. The universe is vast, and we've barely scratched the surface of its possible phenomena. On the other, the Copernican principle reminds us that assuming we're alone is its own form of arrogance. If advanced civilizations exist, their signals might look exactly like this: rare, deliberate, and just strange enough to make us wonder. For now, the Hercules signal remains in limbo, unverified, unforgettable, and utterly unresolved. It's a Rorschach test for how we see the cosmos, a universe of cold, impersonal physics, or one punctuated by whispers we're only beginning to hear. Until fresh data breaks the deadlock, it lingers as both a cautionary tale and a beacon of possibility, proof that some cosmic mysteries refuse to fit neatly into any box we've built. From ghostly nebulae flickering in perfect sync to rogue planets defying gravity's grip, the Hercules Cluster has revealed itself as a cosmic hall of mirrors, where every discovery twists reality just enough to leave us questioning everything we thought we knew. Let's retrace the steps of this journey through 25 of the universe's most baffling puzzles. We began with dark matter's disappearing act, entire galaxies spinning flawlessly without the invisible scaffolding that should hold them together. Then came the phantom radio signals, bursts of energy pulsing without rhyme or reason, as if the cosmos itself were tapping out Morse code. We explored the vanishing dwarf galaxies, slipping into the void without a trace, and the rogue gas clouds fleeing the cluster at impossible speeds, like cosmic renegades breaking free of gravity's chains. The mysteries only deepened. There was the infrared glow with no source, bathing the cluster in heat from an unknown furnace, and the twin supermassive black holes, one devouring everything, the other fasting in eerie silence. We encountered the Starless Void, a desert in a universe brimming with stellar birth, and the gamma-ray burst that refused to die, flaring back to life like a cosmic zombie. The cold spot in the cosmic microwave background whispered of colliding universes, while the runaway cluster core raced ahead of its outer layers as if yanked by unseen hands. The metal-rich void hoarded precious elements like a dragon's treasure, yet no stars ignited there. The synchronized galaxies spun in eerie harmony, defying randomness, and the echoing light of distant galaxies reached us multiple times, their images staggered like pages torn from a timeline and shuffled out of order. We witnessed the warped Einstein ring, bent by forces we can't fathom, and the X-ray halo shrouding the cluster in high-energy light with no clear origin. The redshift anomalies mocked Hubble's law, while the Hercules Great Wall stretched across the cosmos, a structure so vast it challenged the very notion of universal uniformity. And then, of course, the Hercules signal, a radio pulse so unnervingly precise, it straddled the line between natural wonder and something far more provocative. Each of these phenomena isn't just a curiosity, it's a crack in the foundation of our understanding. They force us to ask, are we missing entire chapters of physics? Is dark matter more complex than we imagined? Could forces beyond our current models be sculpting the cosmos in ways we're only glimpsing now? The Hercules Cluster doesn't just defy expectations, it rewrites the questions. So as we close this journey, don't just think of these mysteries as isolated oddities. See them as pieces of a grander puzzle, one that stretches far beyond Hercules, beyond our telescopes, and perhaps even beyond the limits of our imagination. The universe is stranger, wilder, and more wondrous than we've dared to assume. And if these 25 enigmas prove anything, it's that the greatest discoveries aren't just about finding answers, they're about learning how much we have yet to ask. If you're as captivated by these cosmic riddles as we are, make sure to subscribe and hit that notification bell, because the universe isn't done surprising us, and neither are we. The next revelation could be just one observation away, waiting in the dark to rewrite the story of everything. Until then, keep looking up. The stars aren't just points of light, they're doorways to the unknown.